regression. The question is why we use ridge regression. Okay, the most important thing for a ridge regression is to that suppose you have a data set, and in that particular data set you have a high multicollinearity problem. In this data set you have a high multicollinearity problem. Okay, suppose I have a data set. I have already provided the data set to you guys. Suppose this is my data set, and in this data set you can see uh, our dependent variable is expenditure, and it is being dependent on the explanatory variables are income, age, size means family size, and w hours means the working hours. Okay, w hours means the working hours. Now the question is that this data set, when we use this data set, suppose a high multicollinearity problem exists in this data set. Okay, so when we used to regress expenditure on income, age, size, family size, and working hours, suppose there is a high multicollinearity problem. So if there exists a high multicollinearity problem, what should we do? We should, the one of the main option is, we have studied in our UG or PG days that the first thing we should do is you can just drop the variable. You can just drop the variable. Just drop the variable and run the regression again. But what if you need the variable? What if you need the variable, and you need the variable and you need all the variables for the regression? You cannot drop, or you cannot use principal component analysis and everything. You need the variable. So if there is a high VIF multicollinearity problem, so if you cannot also drop the variable, and if you do not want to use PCA, principal component analysis and everything, if from this data, if you see from this data that income, age, size, working hours, these are totally different variables. Age is something like my age is like 38, 45, 60, or income, my income may be of 55,000, 80,000, 60,000. My working hours, the scales are totally different. The scales are totally different, and I cannot create an index. I cannot use principal component analysis. If I want to go for a principal component analysis, what should I do? I should have a principal component analysis by income, age, and size. But I do not have I do not have that option. How should I go for income? Is it sensible for making an index? Like if I make an index with income, age, what should I name that? And is it sensible? That answer is no. That no index shall be created by using income, age, and everything. So what I can do is basically I will go for a ridge regression. So remember, these types of regression, ridge regression, lasso regression, net elastic regression, these types of regression are basically used when you have a high multicollinearity problem. Now, what the ridge regression basically do? Let me show you by an example. Is my screen and my headset or my voice is clear to all of you? Is it okay with you? Okay, okay, fine. Thank you. Now, suppose in case of a normal regression, what we write? We write as y equals to alpha plus beta 1 x1 plus beta 2 x2 and plus beta 3 x3. Okay, fine. This is your regression line. You want to regress y on what? X1, x2 and x3. X1, x2 and x3. Okay. Now the question is, suppose there is a high multicollinearity problem. How can you understand multicollinearity problem? You can just check for, go for the VIF, the variance inflation factor, and you can just check the multicollinearity problem. Suppose there is a high multicollinearity problem among the variables x1, x2 and x3. x1, x2 and x3. Okay, there is a high multicollinearity problem among x1, x2 and x3. So what you will do basically? What you will do? You can just basically drop one variable. If you want to drop x3, you can go for you can write the regression equation as y equals to alpha plus beta 1 x1 plus beta 2 x2. But I want x3 also. The thing is that I want x3 also. I need x3 also in my regression equation, because when you are omitting x3, when you are dropping x3, you are not able to go for the, you cannot capture the effect of x3 on y. If you are dropping x3, you cannot capture the effect of x3 on y. So what you should do? What you should do basically? You should basically include x3 also, beta 3 x3. But if I include x3, the high multicollinearity problem exists. So I cannot use a normal linear regression in this case. I cannot use a normal linear regression in this case. What you can do basically is what you can do basically is you can go for you can go for a ridge regression. You can go for a ridge regression. Okay, what ridge regression basically does? Do anyone know about ridge regression in this class? Anyone? Do anyone know about ridge regression in this class? Anyone? Have any idea about ridge regression? Anyone? The UG guys or the PG guys? Anyone? No, not from you all. Anyone? Okay, fine. So let me just clear it out. So what happens in case of ridge regression? Suppose this variable this variable x2 or x3 is having the most multicollinearity problem is having the most multicollinearity problem. What is a multicollinearity problem? Do you know about what is a multicollinearity problem? You anyone know what is a multicollinearity problem? Hmm. When two independent variables are highly correlated, those are known as multicollinearity problems. Okay, now suppose in this case my x2 and x3 are highly correlated, and it is having a high multicollinearity problem. So one thing is that you can just drop the variable, and another way is that you can run a ridge regression. What ridge regression does? Ridge regression shrink the coefficients. Shrink means this beta 2 and beta 3 are the coefficients of these x2 and x3. The coefficients of x2 and x3 is beta 2 and beta 3, nothing else. So what ridge regression does? Ridge regression just shrink the coefficients. It shrinks the coefficient. Shrinks the coefficient means it actually does do like a it actually do what it does. It actually shrinks the coefficient of x2 beta 2 towards 0, or beta 3 towards 0. Means the variable which is causing a high trouble for multicollinearity, the impact of that variable is actually measured by its coefficient. If suppose beta 2 value is 0.8, how could you interpret it? If the beta 2 value is 0.8, how could you interpret it? You just say that if there is a change in x2 by 1 unit, y increases by 0.8 unit. Is it how you interpret it? If x2 increases by 1 unit, our our dependent variable increases by 0.8 unit. Yes. Any questions from anyone? Have anyone said anything? Okay, fine. So what ridge regression basically does, when ridge regression sees that there are many independent variables and there is a high multicollinearity problem, it basically shrinks means it basically adjusts the coefficient value close to 0. Close to 0 means the x2, the impact of x2 on y will be close to 0. Means when I am yes, yes, yes. The thing is that when you are having multicollinearity problem, suppose you have multicollinearity problem in x2 and x3, with x2 and x3 you have you have many variables, and you have multicollinearity problem. And if you want, if you not drop the variable, you do not want to drop the variable, any of the variables x2 or x3. So what you basically do, you run a ridge regression. Ridge regression, what it does, it shrinks the coefficient. Shrinks means it adjusts the coefficient value. Suppose the value of beta 2 is 0.8, how can you interpret it? You say that when x2 increases by 1 unit, y increases by 0.8 unit. You interpret it like that, no? Now the question is, when there is a high multicollinearity problem with x2 and x3, so what ridge regression does, it adjusts the value of beta 2 and beta 3. It adjusts the value of beta 2 and beta 3. the coefficient of those variables which are having high multicollinearity problem, it adjusts the value of beta 2 and beta 3 close to 0. Close to 0 means the impact of x2 and x3 will become close to 0 on y. You are not neglecting x2 and x3. If you cut the x3 variable from the equation only, you are neglecting the effect of x3 on y. But you do not want to neglect the effect of x3 on y. So what you do, you basically go for some ridge regression, and in that case of ridge regression, it basically shrinks the coefficient value. Shrinks the coefficient value means it adjusts the coefficient value close to 0, means our coefficient value beta 2 and beta 3 becomes close to 0. It becomes converges to 0. Very good. Exactly. The thing is that it exactly converges to 0. Okay, exactly, the thing is that the right term, you use the right term, it exactly basically converges to 0, means it is basically moving towards 0. When how can we determine that x2 and x3 is causing trouble? If we want, if we run a VIF or a variance inflation factor test, VIF test, we can basically see x1 is causing problem, or x2 is having high multicollinearity problem, or x3 is having high multicollinearity problem. So what it does, it basically converges to the variables which are causing problem or which are causing trouble. The variables which are causing trouble, the coefficient of those variables are converging to 0, means those are converges to 0, not exactly 0, but converges to 0, means towards 0. So what will happen, the effect of x2 and x3, what will happen, the effect of x2 and x3 will basically be neglected, will basically be neglected indirectly, not directly, will basically be neglected indirectly but not directly. How, if you want to neglect x3, you can just omit it from the equation, you can drop the variable. But I want the whole variables, I want all the three variables to be included in my regression, so I go for ridge regression. Okay, fine. Up to this, any questions from anyone? When you have a high multicollinearity problem in the data set, when you have a high multicollinearity problem, the first thing we used to do, that we used to drop the variable. We used to drop the variable. This is the first thing we do. We used to drop the variable. Okay, but if we do not want to drop the variable, if we do not want to drop the variable, we want to keep the variables, then we can go for a ridge regression. Any question from others? Have you understood? Then we shall move to Python. Have you understood? Then we can go with Python. Sushmita, Shumit, Shreya, Gulsanara, Orpon, Aporna, others? Yeah, any problem you can tell. Ah, yes, Gulsanara. Hmm. Hmm. Exactly. Effects of those variables are not totally neglected in the model, but partially. Because if suppose in this equation, suppose you can see that beta 1 becomes 0 or beta 2 becomes 0, then what will happen? If beta 2 becomes 0, then what will be your equation? Y equals to alpha plus beta 1 x will be totally 0, will be totally 0. But I am not telling totally 0, I am telling partially converges to 0. I am not using this term totally 0, I am telling that part converges to 0. Okay. Yes, Aparna, what kind of question? Sir, I am having the problem in the equation. If you can repeat it in shorts, it will be more helpful. In which part, Aparna? Beta 2 and beta 2 not equals to, I am not written equals to 0. I told converges to 0. Converges to 0 means it may be 0.1, it may be 0.2, it may be 0.3, it may be 0.4. Means I am going close to 0, not equals to 0. I am going close to 0, not equals to 0. Okay. Okay. Now let me go with Python. Just wait for a moment. I want to open the Jupyter notebook. It will take some time. Okay. Yeah, it's open. Fine. Now, what I do first, I upload my dataset first. Let me upload it desktop. In my desktop, I have kept my dataset Reg. I just open. I just go for upload. Already my Reg is being uploaded. So what I should do? I should cancel. Okay. I open a new Python script. I open a new Python script. Okay. I open a new Python script. Okay. So first what I should do, I should, which library should I call first? Any answer from you guys? Which library should I call first? Yes, the pandas library. Okay. I should call first the pandas library. Let me import pandas as PD. This is my import pandas as PD. I have called the pandas library. What is this pandas library used for? Any answer from anyone? What is this pandas library is used for? This pandas library is used for data analysis, reading the dataset, and many more. Okay, fine. Now, secondly, I will import NumPy as NP. NumPy is another library which I am importing. Now, since I will go for a regression, I will just go for import stats model. This is another library, stats models dot API. Stats models dot API. Okay, this is another library, stats models. Okay, I am going for statistical models, so the library is named as stats models. Stats models dot API as SM. Fine. Now I will just run these commands. These commands, these commands are okay. Now I will go for from stats models dot API. From stats models dot API, what I will do, from stats models dot API, there is, yeah, I am that saying that stats models, yes. Okay, now from stats models dot stats, okay, stats models, yes, this s is missing, thank you. From stats models dot stats dot outliers, from stats models dot stats dot outliers, I will call underscore influence, I will call variance inflation factor. I need VIF. Why I should go for ridge regression at first? First I will check VIF, then I will go for ridge regression. If the VIF is okay, then why should I go for ridge regression? So under this statsmodels.api, there is another library, that is statsmodel.stats.outliers. From this sub library I want to call what? I want to call variance inflation factor. I will write import variance underscore inflation underscore factor. Okay. So why I have called variance inflation factor? This will show me the VIF value. This will show me the VIF value. Okay. Now I run this command. Okay, this no problem. Now under this statsmodel.api, there is another sub library, that is sklearn. Okay, sklearn. Now I will call the sub library again. From sklearn dot linear underscore model, scalar dot linear underscore model, import what kind of regression I am going to perform. I am going to perform ridge regression. So I will write import ridge from scalar dot linear underscore model. So this is another sub library, scalar dot linear model. I am importing the ridge regression. So I will run this command, no problem. Now what I will do, I will go for a standard scalar. Okay, another command you have to write for a standard scalar. Standard scalar is basically used when you just go for the ridge regression and all that, you should scale the variables. Okay, you have to scale those variables, so we will go for standard scalars. So this is also in scalar dot pre-processing. One thing you should know, that you do not have to understand each and every line of the code, because you are not going to be a software engineer or a web developer or a app developer. This is the most important thing. Okay, you guys are going to be an data scientist. What you should know, you should know that what kind of model I am using, when to use what kind of model, and how to interpret those models. You do not need to understand each and every line of this code, that how this code is being generated. I am still giving explanation to each and every code, but you do not have to keep in mind those words, because you guys are going for to become a data scientist, not a software developer or not a data engineer, or not a for engineering purposes. Okay, those people who are app developers, web developers, though those people, they should need all these things. They need all how this code is being written, what is the meaning and interpretation of each and every line code. You do not have to go for that. Okay, you just understand what kind of model we are using, when to use what kind of model, and the most important thing, the interpretation of the model. Okay, now this is another sub library, scalar.preprocessing. We will import standard scalar. Okay, this standard scalar is basically used when you go for a ridge regression. We will run this command. Okay, no issues. Now what we will do, after importing all the libraries, we have imported all the libraries, all the sub libraries, we have completed this part. Okay, now what we will do, we will first recall the data set. We will call our data set. Okay, we write the name of our data set as df. Df is the name of our data set. Then what should I write? I go for pd dot read underscore excel. You know this basically. Since it is an Excel file, I will give the name of the Excel file. What is my name of Excel file? It is ridge. It is basically ridge. And what should be the extension? Excel SX. Okay, fine. df equals to pd dot read underscore excel, and under and in a bracket I will go for ridge underscore ridge dot excel sx. Okay, fine. I just want to view the data set. I will go for df dot head. I go for df dot head. You can see this is expenditure, this is income, this is age, and this is working hours. This is size, family size, and this is working hours. Okay. Now what I will do, I will first run an ordinary least square regression, a normal linear regression, OLS. Then I will check the VIF. If the VIF value is very high, then I will go for ridge regression. Then I will compare between OLS and ridge regression. This is our objective. What is our first objective? To go for a normal linear regression, because we do not know that whether VIF should whether ridge regression is needed or not. If the VIF values are very high, then we will go for ridge regression. Otherwise, we will not go for that. If the VIF values are very high, if there exists a high multi-connectivity problem, then we will go for ridge regression. Otherwise, not. Okay, fine. So we first define x. What is x? X equals to df. What is x? X are my independent variables. Okay, x are my independent variables. What is my first independent variable? Can you say from the screen? My first independent variable is income. Fine. Then what is my second independent variable? My second independent variable is age. Fine. My third independent variable, it is family size. No, x means you write y equals to alpha plus beta x. What is x? X is your list of independent variables. And what is y? Y is the dependent variable. Dependent variable is expenditure. You can see what you write, y, this is your expenditure. And what are the x's? This is x, this is x, this is x. So these are x, these are x, okay, these are x, and this is y. Fine. So size, and after that, what is your last independent variable? It is working hours. Fine. So we have defined x as our independent variables. We have defined x as our independent variables. Now it is time to determine our dependent variable. What is our dependent variable? We write it as y. Okay. Y equals to df, and what is our dependent variable? Our dependent expenditure. So we write expenditure. Under a third bracket, we go for expenditure. Fine. We have defined x as our independent variable. We have given the list of the independent variables to Python. Y as our dependent variable, we have given the list to Python. Okay, fine. We run this command. X and y is being defined. Now I want to go for an OLS, ordinary least square. Okay. So now what is the regression equation? Y equals to alpha plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. Can you say what is this alpha? What is this alpha? What is this alpha? Intercept term, or sometimes we call it as constant term. Okay, in softwares we call it as constant term. So we add an constant first. We add a constant first. X underscore OLS. Under our OLS, x is our list of independent variables, and in the list of independent variables I am adding and interceptor. Okay, I will write equals sm. I will use the library sm. What is sm? Sm is our statsmodels.api. Okay, sm. Fine. So what I do, dot add underscore constant. I will add an constant. If you do not add a constant, it will give you the result without a constant. You will have the regression equation as y equals to beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus cy. Will not have alpha. Okay, but I will add a constant, and under that I am adding a constant. Fine. After adding a constant, now it's time for our model. I will name it as OLS underscore model. Okay, this is our model, and we will write the code. What we will use? We are using the statistical model. Which library should you use? Pandas, NumPy, or statsmodels.api? Which model should we use? We use statsmodel.api. So we will be using the sm. We will be using the sm function. You guys are new, that is why I am just explaining each and every line of code, but I am repeating you several times that writing the code is not a very big thing for you guys. Okay, it is not. Do not remember that sir have written OLS model and I should also rewrite it as OLS model, I should remember it. No, you should not do like that. The most important thing is that you should go for what you should go for. You should just go for the important thing is interpretation of the model, when to use what kind of model and everything. Okay, sm.ols, ols, and under that, what is my dependent variable? Y. I have named it as y, so I will give y first, then I will put a comma. And what are our independent variables? What are our independent variables? Our independent variables are x underscore ols. So I will give x underscore ols. Okay, fine. Oh, sorry, the ols is written as oh, okay. OLS is written in small letter. Otherwise, x underscore OLS, this is written in small letters. Otherwise, it will give me a wrong error. Okay, it will show me as an error. Okay, fine. After that, we want to fit the model. That is why we write fit and opening a bracket, closing a bracket. OLS model, sm.ols. First, we give our dependent variable, then we give our independent variables, and then we write fit because we want to fit the model. Okay, fine. We go to run. Our OLS model is being completed. Now you want to see the summary table. For what you write OLS dot model, sorry, OLS underscore model. We have named it as OLS underscore model. OLS underscore model dot summary, open a first bracket, close a first bracket. Your model is being stored in OLS model. So I want the OLS model summary. I just write OLS mod dot underscore model dot summary. I will run the command. You can see that the OLS model is appeared in your screen. If you want, if you think that this type of, I do not want like this, I want like a very good in a well structured manner, this is also in a well structured manner. You can see the r square is given here, adjusted r square is given here, f statistics is given here, all the things are given here. But if you want that I want in a very good structural manner, you just write print, you just write print, add another command, print, and what you do, you just close the bracket and run this command. You can see if you write add and print, the model result is same. But if you want two structures, if you just do not write print, only write OLS model dot summary, if you just write OLS model dot summary, it will look like this and you have to scroll down and see all the variables. But if you want like the stata format, how it is being shown in stata, if you want that format, just add another line, print, and go with run. Okay, you can see this is our OLS regression result. What we should see first, our probability F statistics. What is our probability F statistics? 2.09 E minus 30 E hyphen 31. Can you interpret what is E hyphen 31? Do you know? Anyone knows what is? No, 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 no. Do you know what is basically E hyphen 31? No, actually it means there are 31 zero before 2. There are 31 zero before 2. So it cannot show you like 0.000000002. So what it does, it adds E hyphen 31. There means there are 31 zero before 2. So if there are 31 zero before 2, so is my model significant or insignificant? How can you interpret? Very good, because it is less than 0.05. It is less than 0.05. Log likelihood, AIC, BIC, these three things are not needed. Python gives you, but these three things are basically used when there exist. These three things are basically used when there exist non-linear estimation process or maximum likelihood. You do not have to see for this log likelihood, AIC, BIC. Okay. Now you go for coefficient. Can you see the income is the p-value of the income? Is it significant? Yes. P-value of age, is it significant? Yes. Size, is it significant? Yes. Fine. And working hours, is it significant? Yes, it is also it is not significant. Now the three variables are significant. There is another, you can know, you know that autocorrelation test, during our classical linear regression model, we have an assumption that it is not autocorrelated. And you can see the Darwin Watson. Can anyone interpret the value of Darwin Watson? Is it autocorrelated or not? Always remember, when the Darwin Watson value is close to 2, when the Darwin Watson value is close to 2, we say there is no problem of autocorrelation. When the Darwin Watson value is close to 2, there is no problem of autocorrelation. Okay. Do anyone know Jarki-Bera test? Jarki-Bera? Can you say anyone? Jarki-Bera? Why it is used? Jarki-Bera? Jarki-Bera means when you go for a regression, you have the error term, and what is the first assumption of the error term? UI is normally distributed with zero mean and sigma square variance. Okay. Okay, fine. How does a normal distributions look like? It is like a bell shaped. It is look like a bell shaped. So fine. So in Jarki-Bera, the null hypothesis is normally distributed, and the alternative hypothesis is not normally distributed. Okay. So can you interpret that What should I accept, null or alternative? From the probability JB, Jarkibera, what should I interpret? The null is accepted or the alternative? In case of we, there are three assumptions. The first assumption in a linear regression model is expectation of u equals to 0. This is our first assumption. Then covariance of ui uj equals to 0. Okay, now in case of covariance of ui uj means there is no autocorrelation. But how can you interpret from the Darwin Watson? What is the value of the Darwin Watson? 2.174. When the value of Darwin Watson is close to 2, when the value of Darwin Watson is close to 2, you can say there is no autocorrelation problem. So you can say no autocorrelation problem. What is our first assumption? Basic assumption. Our UI, the error term, is normally distributed. So for the, we have to check for the normal distribution or not normal distribution. Our data is normally distributed or not normally distributed. For that we used to conduct one test that is known as Jarkibera test. And in this Jarkibera test, the null hypothesis is our data is normally distributed and the alternative hypothesis is not normally distributed. Can you say from the data that what should we accept? Because we have, it is 0.603, so our null hypothesis is being accepted. Okay, fine. So Python actually gives you a lot of things which data doesn't gives you. You can see the or many times, many times. Okay, so fine, now we should move. Is any problem up to this? Any problem up to this from anyone? Any problem up to this from anyone? Any questions, any problem? No sir. Just remember these types of interpretations. The first interpretation is we have to go for Darwin Watson. No autocorrelation assumption. We assume that there is no autocorrelation. So when it is close to 2, you can say that there is no autocorrelation. Then Jarkibera. In Jarkibera, what is the null hypothesis? Normally distributed, our data is normally distributed, and alternative hypothesis, it is not normally distributed. We can see that it is not normally distributed. In case of, it is normally distributed because it is 0.603, means it is greater than 0.05. We will accept our null hypothesis. So it is normally distributed. Okay, fine. Now we will go for VIF. We will go for VIF. We write VIF equals to PD dot, we go for VIF equals to PD dot data frame, and we will give a first bracket and we will close a first bracket. Okay, and after that we will write VIF, and in a third bracket we will give variable. I want to check VIF on the variables. Okay, variable on which column? Variables on which columns? There are two, one is y and one is x. I want to check for x or y. X, exactly. So I will write variables equals to x dot columns. Fine, x dot columns. And then I will again write VIF, then under in a bracket VIF will be equals the variance inflation factor. So I have to open a bracket. We have already called the variance inflation factor from stats model dot outliers. We have already imported the variance inflation factor, so do not have to import it again. So I write variance underscore inflation underscore factor. Okay, fine, underscore factor. Okay, now I will give x dot values, our x values. Okay, and we have to give a I. This I means when you write, when you write, suppose you write like this, yi equals to alpha I plus beta 1 x1 plus, it is what this I means, or beta I xi. What this I means? This I means when I equals to 1, the observation 1. Okay, when I equals to 2, when I equals to 3, like this. Okay, so suppose you have a data set of 500 observation. So yi equals to alpha plus beta xi. So means when I equals to 1, I am running regression for observation 1. When I equals to 2, I am running regression for observation 2. So what I do, I basically write an I, x values comma I. I means basically the range. Okay, the range, the total range. So what I will give, I will give a range. Okay, I will give a range. Right, for I in range, the total range, the whole range, x dot shape, x dot shape, and in a bracket you have to write for 1. Okay, now for we run this command, we just see that all the brackets are being closed, one third bracket, one first bracket, and one third bracket. Okay, fine, we just run this command. Okay, there is no error in this command. Fine, now I will go for the VIF. I will check the VIF values. I just write VIF. I will check the VIF values. I run. Can you see that what was the rule of thumb in VIF? What was the rule of thumb in VIF? Can anyone tell me what was the rule of thumb in VIF? When we have done regression, we already told you. What was the rule of thumb in VIF? Hmm. Or if you or if you see individually, there is no mean VIF here. If you see individually, if the VIF value is greater than 10, then there is a problem of high multicollinearity. Can you interpret that whether multicollinearity problem exists or not? High multicollinearity problem, because the higher the working hours, the higher the income. These two are correlated. The higher the working hours, the higher the income. The higher the age, the lower the working hours. These are also very correlated. The higher the age, the higher the income. These are also correlated. So from the VIF table, if the VIF value is greater than 10, then we can say there is a high problem of multicollinearity. So in this case, our VIF value is 15, 13, 17. So we can say there is a problem of multicollinearity. So what we have to go? We have to go for a ridge regression. We have to go for a ridge regression. Fine. So we go for ridge regression. I write ridge underscore results, ridge underscore results equals to pd dot data frame and pd dot data frame. Okay, fine. Now what I have to do, I have to give a first bracket and a curly bracket, means a second bracket. Okay, under that what I have to go, I have to go for, oh, one thing I have missed. Very sorry. Okay. One thing you should first scale down for ridge regression. You remembered that we have gone for a scalar. Okay. A standard scalar. For ridge regression, we have used a standard scalar. We have to scale first. We have to scale first. Scale means we are scaling the variables. Scale means we are scaling the variables. So what we do, we basically write ridge equals to ridge, and under that alpha equals to 1.0. Alpha equals to 1.0 means what is your alpha? Your intercept. We are telling that our intercept is 1.1. Okay, so we are telling it will appear something like else also. It can appear something else also. The intercept may be 0.01, it may be 0.05, it may be 0.8, it may be 2, it may be 3. Okay, we are scaling. Okay, now what we do basically, after that we just reach dot fit, and under that what we do, we basically x, we are scaling. Which variable should I scale? The independent variables. I will scale the independent variables. X underscore scaled, x underscore scaled comma y. Okay, I am scaling the x variables, so I go for this. Okay, fine. X scaled is not defined. Okay, there is a problem. Okay, let me write another line of code, because scalar is imported but scalar is not imported properly. So what we write? Anyone wants to join? I think. Okay, already joined. Fine. So why the error came? See, the error came basically because I have not scaled yet properly. I have imported the scalar function. I have imported the standard scalar, but I have not imported. I have imported the standard scalar, but I have not scaled this. I have not given a name to the standard scalar. You can see, you have imported the standard scalar. In this case, you have import pandas, but you have given a name PD. Import numpy, you have given a name np. Import statsmodels.api, I have given a name sm. I have imported standard scalar, but have I named scaled? Have I named it at scale or scalar anything? So it is not being read it. Okay, so first why we just give the name. Scalar equals to standard scalar, and in a first bracket open we have given the name as scalar. Okay, we give the name as scalar, and then x underscore scaled, x underscore scaled, and we just write scalar dot fit. X underscore scaled, we just write scalar dot fit. We want to transform the x variables, we want to scale the x variables. So what command we should use? We will use the transform function. Scalar dot fit underscore transform what? Transform the x variables. So we will give x. What are our x variables? We have defined the x variables. It is basically the income, age, size, and working hours. Okay, now this command will, I will run this command. Again it is showing some types of error. Standard scalar, standard. Okay, I have written the spelling wrong. Standard, it will be dard, standard scalar. Now run this command. Yeah, now it is being run. Okay, I have written the spelling wrong. Okay, so standard scalar. Now I will just copy this command and I will paste it. Now this command will work. You can see now this command will work. Okay, the reach function appears. The reach function. So what is the, what error was why we are making? The error was that we have imported the standard scalar function library, but what we have not done, we have not given a name to that. So that's why Python told me that x scaled is not defined. Suppose if you write pd but you have not given the pandas library as pd, so it will show me that pd is not defined. So it was not being defined. Now it is being defined and the reach function appears. Now we will go for the reach. Okay, first I do reach. Okay, first I go for the reach regression. Reach underscore results, this is our model, reach model. Reach underscore results equals to pd dot data frame. Pd dot data frame, you have to open a first bracket, under that a curly bracket, because I want to give the variables, the x variable, I have to give the variables. So what you write, you just, if you want you can go for another line because this line becomes very big. So what you do, variable, you just write variable, and under that which variables I want to go for the x variables, because the multicollinearity problems is not in the y variable, because y is our dependent variable. The multicollinearity problem is in the x variables. So I will go for the x columns. Okay, I will go for the x dot columns. I will go for x columns, and after that I will give a comma, and what I do, I basically go for reach. I go for reach underscore coefficient. I need the coefficients. I need the coefficients. So I read the coefficients. Okay. Coefficient, fine. What I have written? Reach result. This is my model. PD is the data frame, our data frame. From the data frame, the variables are x column, and I need the coefficient of which, the x variables, the coefficient of which, the x variables, income, age, size, working hours. I do not need the coefficient of expenditure because it is the dependent variable. So you have given x columns, you can see you have given x columns, and what you need, the reach coefficients. Okay, and the column will be named as reach coefficient, and what I need under that, I need the reach coefficients. I need the reach coefficients, means reach regression coefficients. So reach dot coefficient. Okay, fine. So you have given, you have written this comment, fine, no problem. You have to close these two brackets. The two brackets are already closed. I just run this comment. Again it is showing me reach is not defined. Have I written a wrong code? Just let me check once. Reach. Let me check once. Coefficient. Okay. Coefficient. Okay. So the thing is that you just see the error. Reach coefficient is the name of the column. Okay. And what Python is telling, reach object has no attribute coefficient. This is a very interesting thing. This will make you learn. Okay. Reach attribute, reach object has no attribute coefficient means reach regression coefficient, there exists no function named coefficient. The function is actually coef. The function is actually coef, coef. I have written coefficient here. This is the name of the column, so I have written coefficient. But this is the not the column. This is the name of the function. I have written coef. So I will run again. You can see there is no error. I have written coefficient. So coefficient, there is no function like coefficient. I have to write coef. Coef is the original function. Coef. Okay. So from the error you learn a lot. This is the basic thing. Okay, from the error you learn a lot. So our ridge regression has been done. So our ridge regression is being stored in what? Our ridge regression is being stored in ridge underscore results. I will just copy this ridge underscore results and I will just paste it and I will run. You can see the ridge coefficients appeared. You can see the ridge coefficients appeared. Okay, the ridge coefficients appeared. So from OLS, you can compare from OLS what was the value of coefficient of income 0.6151, and in case of ridge it is 6735. In this case the value of age is minus 307. In this case the value of age is minus 3393. So when to apply ridge regression, the basic thing is that when you use ridge regression when you have a high multicollinearity problem, when you have a high multicollinearity problem. So in this case you see that when you go for a OLS, after that when you check the VIF there is a high multicollinearity problem. So after that what you have done, you go for a ridge regression. You go for a ridge regression and the ridge regression results, the ridge coefficients appeared here. This is basically multicollinearity free regression. Now you can, yes, once again, once again, I cannot hear you. You do not have to take screenshot. The video will be available to you. The video will be available to you. It is being recorded. Okay, it will be available to you. Okay, do not worry, just understand in the class. The video will be available to you guys. Okay, now we want to compare between the OLS coefficient and ridge coefficient side by side. So we just write OLS coef. So under the OLS model, we have already run the OLS model and we have to give the parameters. Okay, I just want another column. The column will be named as OLS coefficient. So I am just calling in that, you can write this command, or if you are practicing with me you can write this command, or you will get the video, you do not have to worry. Okay, and we have to give the reset underscore index. Okay, underscore index. I want another column. We will compare between the ridge coefficient and the OLS coefficients. Okay, so under that we will write OLS underscore OLS coefficient, OLS underscore coef, and dot columns equals to, under that we will give the variables. That is our variable, and under that we want the OLS coefficient. So what we will write, we will write the OLS coefficient, OLS underscore coefficient. Will be the name of our, this will be the name of our column. This is ridge coefficient and we will generate another column, that is OLS coefficient. Okay, coefficient. Fine. Now we want to compare. First we run this command. Oh sorry, again I have written OLS coefficient somewhere. OLS coefficient. OLS coefficient. Have I written any wrong? OLS? No, that will be fine. That is fine. That is not. It is telling me OLS coefficient is not defined. So okay, fine. Let me run this command first, and then run this variable. Let me check once. This v will be greater than, and let me run. No, there is something error. Let me check. No, that is also not the case because OLS coefficient. Okay, 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 okay. There will be a very small thing. There will be a colon. There will be a colon. Okay, there will be a colon. Okay, fine. So when you write reach coefficient, it you have given a colon, a same double invert double colon in both the side. So I have not given the double colon in both the side. Okay, now it is being. The errors are very small, but you have to look for that. What is basically the error is. Now we will go for comparison. Our comparison, we will go for comparison. We will merge. What we will merge? We will merge this table with OLS table, with this OLS table, this coefficient table. Okay, we will merge. So we will write pd dot merge, pd dot merge OLS underscore coefficient coef. Our it is named as OLS coef. So OLS coef and what, comma, reach results. I want to merge the reach underscore results. So you go for reach results. You can see OLS coef, it is the name OLS coef. You will merge this with what, reach results. This is your reach result, this with this column. Okay, so we just reach results on what, on which ground, on what, on which ground you will merge, on which ground, on variable, on the ground of variable, because you have the variables. Okay, fine. So we will run this command. After writing this command, where my comparison is being stored, the name is given as comparison. I just click here, I just copy paste and run. You can see now, see the OLS coefficient and the reach coefficients are side by side. The OLS coefficient and the reach coefficients are side by side. You can see. So what are the things you have to check when you go for a normal regression? First you go for a normal regression. Okay, and then what you do, you basically go for a multi-cognitive problem, because from this data you can basically understand there may be a multi-cognitive problem, because income and age, it is highly correlated, because higher the age, higher the income. Income and working hours, it is also correlated, because higher working hours generates you higher income. Okay, so what is the thing? The thing is that when you see that there may be a multi-cognitive problem, you first go for a normal regression, then go for a VIF test. After going for a VIF test, you can see that there is a high multi-cognitive problem. You can see from the data that is there is a high multi-cognitive problem. After that, you go for a ridge regression. And after you go for a ridge regression, you just compare the OLS coefficient and the ridge coefficients, that how they differ. This portion is not basically needed. Okay, I have just showing you for the comparison part, but you do not have to compare all the time. From here also you can compare. You have the ridge regression result here, you have the ridge regression result here, and you have the OLS regression result here. So you can compare from here also. This part portion is not always needed. Okay, so now it is time to get questions. Any questions from anyone? Now it is time to get questions. No sir, clearly understood. Others please. Okay, thank you, Sumit. Thank you, Adrita. Someone understood, sir. Apurna, thank you. Others, Gulsanara, Shreya, Moua. and Orpon and Shushmita. Understood, guys? Is it okay? No problem, sir. Okay. Others, Apurna. Oh, Apurna told me. Gulsanara, Mohua, Shreya, Shushmita. Is it okay with you? Okay, understood, sir. Understood, sir. Yeah, any kind of doubts you can just share with me. Have understood part. Okay, yeah, you have joined a little bit late. Okay, fine. So thank you, guys. This will be provided to you via recording. Okay, so thank you, guys. And there will be a second session that will be on, I think that will be on net elastic regression. Okay, that is also a series. This is a series: ridge regression, net elastic regression, lasso regression. These are being series. Okay, so next part will be on net elastic regression. Fine. So thank you, guys. Thank you.